here now. So welcome back, everybody. And the topic this week is a new one, and we're going to start what we might call for real machine learning. So what I call the low-level type of machine learning, it's like with neural networks, logistic regressions, are methods where you, in principle, can actually calculate analytical expressions for linear regression, ordinary squares and ridge. You can find an analytical expression for the unknown parameters of the model. So these are methods where you might ask yourself, where is the machine learning here? But we use these methods because they contain many of the basic statistical interpretations. They contain many of the basic elements which we encounter in more advanced machine learning methods. And now we're going to dive into neural networks, and that's going to keep us busy for the next month. And the plan is to cover neural networks. We are going to, in project number 2, we are going to write our own code for a neural network, and it's pretty useful to demystify what it actually means. With that, we are going to move on to what's called a convolutional neural network, which is the kind of standard methods for imaging. And then we are going to look at the analysis of a topic which is called time series, which many of you may encounter. You often have made measurements over different times. And this is called normally recurrent neural networks. We are not going to dive into more advanced methods because we do have courses which are run in the spring semester which cover more advanced methods. So we have to be a little bit careful with the credit overlap. Now, but before we dive into neural networks, I just wanted to give you some few messages here. Now, one, I wanted actually to give a small reminder of what we did last Friday and last Thursday about optimization. So this optimization doesn't sound like a very exciting topic, right? So I actually love optimization problems, but it's not the kind of topic which excites us that much. But it's needed when you deal with all kinds of machine learning methods, because at the heart of the machine learning method, there is an optimization problem. So for those of you who had problems with the wireless and you were online last Friday, I have recorded the lecture again, so you will find the video from last Friday together with the notes. But there are some small things which I wanted to bring up, and we will also bring this up tomorrow when we are going to present project number 2. Now, concerning project 1, there are many of you have been asked whether we could extend the deadline a little bit, and you probably understood that I am not very much against that. So I thought of suggesting that we could have, so for those of you who have handed in, there's a possibility to revisit it and just tinker and think about what you've written. But I thought of extending it to either Tuesday or Wednesday next week. Now, I'm trying to be a little bit more hesitant to bring a too long extension because many of you are having midterms next week. So next week is actually, for those of you following a bachelor program, there is a typical week which is set aside for midterm exams, and that's next week. So we have to be a little bit careful with, because if we give a too long extension, that may interfere with what you're doing with the midterms. So if Wednesday next week is okay, or let's say Tuesday evening, and because then we can start looking at project number 1 when we are at the lab on Wednesday and Thursday next week. No, project 2. Is that something which can be of use? I'm going to send an email to everybody. So you will find that the extended deadline on Canvas. And if you already have finished, there's always time to resubmit. If you keep in mind again that you can just submit the GitHub address if you're using GitHub or GitLab or Bitbucket, as long as we can access the files. That's the most important thing. Any questions about these things? Yeah? Say again? Regular labs? Yeah, exactly. Okay, so the thing which I wanted to do now before we move on is to give you a quick recap of what we did last week. Just a very quick one. I just need some five to 10 minutes. And the reason why I do this is because in project number 2, since you are going to write a code for a neural network, and there's also going to be a smaller part with a logistic regression, so you can compare a classification problem with logistic regression and a neural network, we need to implement a gradient descent method, because now it's a time when we are not going to, it's like we being thrown out into deep water, because we don't have a nice analytical expression for the unknown parameters, but we have to find them in an iterative fashion by actually calculating gradients and optimizing these gradients. And as I said last week, there are 2 main issues. One, if you have tons of data points, is actually calculating the actual gradient, which can require quite many floating point operations, because you end up with matrix, and matrix vector multiplications, and these are CPU consuming. So you require a lot of floating point operation. And one of the things which we did then last week was to introduce stochastic gradient descent. So that's a way to evaluate the gradients in smaller batches, and they require less floating point operations. So the stochastic gradient descent is a way to actually reduce the floating point expenditure which you would have by calculating the full gradient, by running over all the data points you have. So that's one thing to keep in mind. Now, then, since we don't want to calculate the so-called Hessian matrix, which is the second derivative of your cost function, and remember that what we have done is to truncate a Taylor expansion of the cost function at the level of the second derivative. With that, we get Newton's equation for finding the optimal parameters. That involves a second derivative, which is in our case is what we call the Hessian matrix. And we have to invert that matrix. And we typically don't want to do that. And that leads to this new parameter, which is called the learning rate. So for the learning rate, we have different ways to tune it. One, just leave it as it stands, just a constant. We have some linear ways. We can tune it in an exponential way as a function of the number of iterations we make. Or we can use what's normally called momentum gradient descent or momentum stochastic gradient descent, which keeps track of the memory of previous iterations. And then we can go to second order methods like adaptive gradient descent, which is called ADAGRAD. We have root mean square propagation, and we have ADAM, and we have many, many other methods. And as I said, in a way, jokingly, is that if you can cook up something which is more efficient than what we have, I mean, you will get many friends, really many friends. These are friends which will cite you. They may not be the friends you want to have, but they will cite you. And this ADAM, if you look up the number of citations it has more than 100,000 citations. That simply tells you how important this kind of bottleneck is, the optimization part. So let me give a quick reminder of some of these things which we discussed last week. So let's bring back the whiteboard and take a quick look at these methods, and then we're going to jump back to the Jupyter Notebook and take a look at how we can encode these things before we then move into neural networks, which is going to keep us busy for the next month. So let me quickly say something about gradient methods. So what we did was to truncate the Taylor expansion of the cost function around a new iteration at the level of second order. And that gave us an expression for the unknown parameters at iteration n+1 in terms of the previous one, n. And then we have minus, and then we have the second derivative, which is this Hessian matrix calculated at this beta of n, and multiplied with a gradient at iteration step beta of n. So this is the basis. And we, since normally the matrix H and the gradient itself can be quantities with large dimensionalities, depending on how many features and how many data points we have. We would typically approximate the calculation of the gradient and also the calculation of this Hessian. So the typical approach which we do now is an approximation. So we would have h minus some gamma, which is our learning rate at iteration n, multiplied with the gradient at iteration n. And this is the quantity which we called the learning rate. And we have two main things. One is an efficient calculation of the gradient. And this is something which led to what we call a stochastic gradient descent. And I'm just using the acronym GD for gradient descent. So that's the one of the steps which you will have to implement in project number 2. And the first part of the project deals with a linear regression problem where you can invert the matrix, and we are going to look at a simpler function. If you want to use a Franke function, you can do that, but we are going to look at a simpler function just to get acquainted with the gradient descent methods. And then you can compare that with standard linear regression where you invert the matrix and get the coefficients beta. So gradient descent is one of the basic methods, and the stochastic gradient descent is a standard implementation. And then we have what we will call learning rate, what we can call scheduler or learning rate tuning. And in this case, we can have a learning rate which has a linear function in terms of iteration, linear gamma k n in terms of iterations. That introduces some constant in terms of iterations. N. We can have an exponential one. So, and all these imply some coefficients which we need to set up. So we would have a new set of parameters. So the learning rate is now a parameter which we can tune in order to get the best possible root mean square, for instance. You can have an exponential one. You can just keep it constant, and another. I just put other here. I'm not going to list everything which we went through last week. But then we have what's normally called second order approaches. Actually, with the efficient gradient evaluation, we also have something which is called a momentum gradient descent. So stochastic plus momentum. I forgot that one. Momentum GD. That's independent of the way you treat the learning rate. And you can mix all these things. You can do a stochastic gradient descent with an root mean square propagation for the learning rate. You can have a linear learning rate. You can have an exponential learning rate. You can do a mix of momentum and stochastic gradient descent with a method like ADA-grad or root mean square propagation. And then we have these other methods which are the adaptive ones. So one of them is ADA-grad. And we had this RMS prop, root mean square propagation. These are the most common ones. And then we have ADA. So in the lecture notes last week, we actually presented codes which do this. So let me quickly just remind you of how you can program it. So if you look at this ADA-grad, root mean square propagation, and ADAM, they are kind of mixtures of finding an approximation to the Hessian matrix. So one of the things which we found, and let me just bring this up, we did something last week which was called the steepest descent. Now in the steepest descent, we had an adaptive learning rate, which we found was equal to the transpose of the gradient at iteration n multiplied with the gradient divided by the gradient at iteration n, the Hessian matrix at iteration n times G at iteration n. So in the steepest descent, you can actually calculate the learning rate according to each iteration. Now, one of the things which is interesting here is if the gradient is the eigenstate of the Hessian matrix, because then the learning rate will just be the inverse eigenvalue of a given component. So just keep that in mind. So if the gradient is an eigenstate of the Hessian matrix, then this relation simplifies to just the inverse eigenvalue. And that's something which is used in methods like the conjugate gradient descent. But everything you see here requires you performing a vector multiplied with a matrix times a vector. And that requires a lot of floating point operations, in particular if these are large matrices and large vectors in dimensionality. But if you look at this expression here motivates some of the methods like Ada-Grad, root mean square propagation, and so on. So if you look at the Ada-Grad, which we discussed last week, so in Ada-Grad, we actually want something which becomes a vector. And then what we typically would do then is that this gamma of n is something which we made proportional to the inverse of g times g of t, and this is calculated at iteration n. And then, for simplicity, we just take the diagonal matrix elements and just invert that one. That's the simplest implementation of Ada-Grad. So you compute the matrix because G times G transpose is an outer product. You take the diagonal ones and then you have a vector. And then you just need to invert that one and then multiply that with the gradient. That is Ada-Grad. So what you will see is that all these methods here try in one way or the other one to mimic some of the more, how to say, exact ways of doing the iterative process. Like when you do steepest descent, you do actually have a simple but almost exact expression for the iterative update of the learning rate. So this is Ada-Grad. The other methods, you can bring in momentum, where you have some memory of the previous step. You can do additional manipulations like Adam. So let's just quickly take a look at what these methods, how these methods can be implemented. So just keep this in mind, that in this Ada-Grad, the learning rate is now given by, is proportional by the inverse of this matrix, and you take only the diagonal elements. So what I'm going to do now is just to bring quickly back the Jupyter notebook, which we went through last week. So what you will see now are just the slides from last week. And if you go to the end here, so the main reason why I'm bringing this up is not only because this is an important aspect, and as I said, it's perhaps not the most exciting thing we're doing, but it's something which you will need in project number 2, when you're going to write your own adaptive method for the gradient descent method. So the other thing which we recommend is to use automatic differentiation, which allows you to calculate derivatives numerically to numerical precision. So that's one of the things which I also invite you to take a look at. And in the examples at the end here, so at the very end of the lectures, you will find implementations of ordinary least squares, but you will also find the implementation of momentum gradient descent. And then actually nothing can compete with Newton's method, as we mentioned last week. And here you simply take the inverse of the Hessian matrix. And if you do that and you run the calculations, what you will see is that if you have the inverse, I mean, after one iteration, you're just having a gradient which is equal to 0. So that simply tells you that if you can calculate the Hessian matrix, this is a case with a linear function, as you can see here. So that means you have only two parameters, beta 0 and beta 1. So that means that the Hessian is a 2 by 2 matrix. It's very easy to set it up. It's the second derivative of the cost function. And in this case, linear regression is simply the transpose matrix times the matrix X. As you can see here, this is your transpose multiplied with X, with a matrix design matrix. And in this particular case, you see now how fast the iterative method is with the gradients. And I'm using AutoGrad to calculate the gradients, as you can see here. And when you develop the code for project number 2, this is also one of the things we invite you to test. Now, for linear regression, this seems like an overkill, because in linear regression, the gradient is nice, has a nice expression, it's easy to code. But when you come to neural networks, I mean, your gradient is gonna be nasty. It's an ugly quantity. And then using the automatic differentiation is extremely useful, and it saves your day. And it's a kind of way of, because there is, how to say, if you calculate the derivative once, there's not much insight in recalculating derivatives again and again. So if you can leave that to something like automatic differentiation, use it for what it is worth. And here you see clearly that if you have the Hessian matrix, if that is possible, this is what you would prefer to use. So your learning rate now is the Hessian matrix, the inverse of the Hessian matrix. Now what we've done here is actually stochastic gradient descent with AdaGrad, or no, this is first the stochastic gradient descent with automatic differentiation. So it's the same function, as you can see here. So you have the 4 and 3. And if we just leave out the noise here, so let's just take away the noise. So that means that we should get exactly 4 and 3 as parameters. So there is one case here where I set up my own matrix inversion, as you can see here, the pseudo-inverse, as you've been doing in project number 1. And then I do the gradient descent here, standard gradient descent. And then I have the one with a stochastic gradient descent, where I now have to define the number of epochs, the number of times I loop over all the small batches. So every gradient calculation here now contains only 5 points out of 100. So that means that the evaluation of the gradient is actually very, it's with only 5 points, you don't need that many floating point operations. And then we just break it down into smaller batches, and then we collect the final batches, and that is 1 epoch. And then we repeat. And you can see now if I run this, since I'm doing a stochastic gradient descent, so when I do my only gradient descent, I have a good learning rate, no tuning of it. You can see now that I get exactly the same as I get by inversion. But then you see that the gradient descent is not exactly 4, and it's not exactly 3, but still it's getting pretty close. Now, one of the things you will have to play around a little bit with in project number 2 is the new parameters, the number of epochs and the number of batches. Here, we have also a learning rate with a schedule, and this has some parameters. So in this case, it's not an exponential, it's not linear, but it's something which contains a 1 over the number of iterations plus a parameter T1 here. And these are parameters which you can play around with. And you will find in the literature, you will find tons of ways of doing that. Now, if you now go to, you can add momentum gradient descent to this, and that normally reduces the number of iterations you need to converge the gradients to 0. So you're driving the gradients to 0. That's your convergence criteria. And you want obviously all the gradients to go to 0. Some may go fast and some may go slowly to 0. So this example here is an example where we now do momentum, and then you simply have this change which now keeps track of the value from the previous iteration. And that normally speeds up. But here you have AdaGrad. So take a look at that. So in project number 2, so one of the reasons why I bring this up is that I want you to code one of these methods and just get some feeling. Because typically people would use either AdaGrad, root mean square propagation, or ADAM as ways to tune your learning rate as a function of the iterations. And what you're trying to do is in a way to mimic the calculation of the Hessian in one way or the other one, without calculating it. So AdaGrad, and the code which you see here, contains own inversion. Actually, in this case, I actually run through 10,000 points. I gave it a little bit heavier case. Now, what you would do now is if you do stochastic, you don't need to do stochastic gradient descent. You could do a plain gradient descent. So whether you do stochastic or gradient is up to you to decide. And if you add momentum, that's just an additional feature. But AdaGrad, the way you do it now is that over the epochs here, you set up the iterated value. So this is the accumulated value. And this is where you see now the gradients multiply with the gradients transpose. So this is a matrix, this G iter. And in this case, I've changed the function to a function which has intercept 2, slope 3, and a second order term 4. So when I do the fitting here, I should get 2, 3, and 4 as values for the parameters beta. And when I do standard linear regression with matrix inversion, I'm just spot on. So when I use AdaGrad, so I have 10,000 points, I just made the case a little bit heavier. There is a parameter delta in order to avoid possible division by 0. Now I calculate this gradient times the gradient transpose, so this is a matrix, but now I keep only the diagonal one, the diagonal matrix elements, and I take the square root of them, and this becomes a new vector, and I multiply that vector by doing what's called the Hadamard, so component by component of the vectors. So it's not an inner product. So I take this inverse and multiply with the gradients, and then I look at the update. So the update is because now you see that I would typically feed in a learning rate eta here, and that learning rate eta is the one I would start with. And you would typically run this over many learning rates as a guess. And then you have this AdaGrad to adaptively change your learning rate. And you can see, yeah.
Is the diagonal of gradients times gradients transposed, not just gradients squared?
You could actually write it as gradient squared, correct. That's correct.
Isn't that much more computationally efficient?
Say it again.
Isn't that much computationally
Yes.
efficient?
So the way you would actually code this, so what I've done here is actually to set it up the way you would see it described in different textbooks. But the way you would implement it is actually, as was said here, by the gradient square. So what I did here was simply to follow. If you go into that textbook by Goodfellow and company, this is the way they would present the algorithm, but it's not the way you would code it efficiently. So normally, this is another thing, when the codes you will see, if we have an algorithm which is described in the textbooks or in the lectures, I try to follow the way the algorithm is described. But then clearly, the kind of speedier way of doing that is as was said here. So what you would have now, if you take a look at here, you see now that you're basically spot on with AdaGrad. So these are the kind of things I want you to test. There is also a code for root mean square propagation below here. So I invite you to take a look at this textbook by Goodfellow and Benjo and Corwell, in particular their chapter 8, because they have a pretty nice discussion of the different optimization approaches. And keep in mind that there are many kind of ad hoc approaches and other ones which try in a way to mimic the way the learning rate should be changed iteratively. And there's a lot, this is actually a field with a lot of research and many both ad hoc methods, but also more advanced ones. And you might think, why should we spend so much time on optimization? But it's actually at the heart of everything we do. And sometimes you pick parameters which may not converge at all. So another reason why we do this is that in these courses here, we want you to see the pros and cons of the different methods, so that you don't think of these as black boxes. I think that's an important aspect, because many of you may actually be in a situation where you're going to develop new methods, and then having an understanding of where the bottlenecks are is actually very important. Okay, so what I want to do now is to move over to the new topic, which is about neural networks. So I'm going to stop sharing here, and then I'm going to go back to the whiteboard. Oops. So this becomes our next topic, after we've done or gone through some of these more, how to say, low-level machine learning methods. And what I want to do now is to give you some of the basics and some of the elements which we can use in order to understand how a neural network is actually set up. So I'm going to go through in simple steps in case you're not too familiar with neural networks. Now, in neural networks, there's something which is called the universal approximation theorem. So how many of you have heard about the universal approximation theorem? Okay, one of you. Two, okay. Now, the universal approximation theorem is actually something which is similar to what you would have if you have approximated a function with, let's say, Fourier transforms. So many of you are familiar with Fourier transforms. Okay. And then you know that we can actually make, with a given Fourier transformation, we can actually make an error estimate of how good the approximation is. So that's a typical approximation. So a given mathematical theory like Fourier transforms gives you an error estimate because you would truncate your Fourier expansion at a certain level. Now, if you think back to project 1, what you have done is you've taken a function f of x and you've approximated that with a polynomial. And you can now think of taking the absolute value of your error. And that would be an estimate of what your error is. So for some types of functions, you can actually make an estimate of what the error is for what you leave out. Now, what the universal approximation theory says, we are not going to prove it because that's a tour de force in real analysis. And I guess not everybody has taken a course in real analysis. But what it says, and we are going to see examples of it, it says that you can approximate a continuous function f of x with a neural network which has one hidden layer. It doesn't say anything about the number of hidden layers, about the ways you treat the number of nodes or neurons in a hidden layer, and so on. But it says simply that you can approximate a given function to a given precision with a hidden neural net, with a hidden layer. So now, as I said this, I need to explain to you some of these things. And we are going to look at some simple examples which some of you may have seen before. So let's try to baby step ourselves through the introduction of neural networks. So let's look at a very simple case. And this is a graphical representation of what we have done till now. A simple case. So we have some inputs, x1 and x2. These are input to a specific function, and these yield some output y. This is a graphical way of representing what we've been doing in project 1. And ideally, what we have is a function here, which we might call f of x1 and x2. So one of the things which we have assumed in linear regression is that there is a function f. In a certain sense, that is a model for linear regression as well. We don't know this function f of x, and we approximate that with some kind of function, a polynomial. It could be a function of sines and cosines or whatever. But the assumption which we made is that there is a function. So we feed in something and that spits out something. Okay, so this is the way you would represent this graphically. And we are going to use that a little bit in the notations here. Now, what we are going to do now, besides assuming that there is such a function, we are going to make some changes of variables. So we are going to rewrite this now. So this y is now going to be replaced by a new symbol, t. So that's my target. And you will often see that we talk about the values we want to reproduce as the target values. Then I'm going to assume now that this f of x1, x2, or f as a function of these different parameters, and I'm just rewriting this in terms of an f of x, I'm going to replace that one with a function which I'm going to call sigma. And I'm not going to specify yet what it depends on. Then what I'm going to do now is to replace the parameters beta, which we had, with a general parameter theta, and I'm going to specify what it may contain. So I'm going to make a simple model now, still with x1 and x2. And then we're going to stay a little bit along with a simple vector x, which takes only two values. So what we're going to put in here now is something, we're going to rewrite that graph, which we put in a slightly different way. So the graph is now going to look like this, and then we're going to also present a more compact way of putting it in. So this is x1 and x2, and I'm going to call this the input layer. Then, in this specific case, I'm not going to have a hidden layer, but there's going to be something which modulates the values x1 and x2 into this function sigma. So I'm simply going to write this as a sigma. So here I have this function sigma, which does something with the input which comes in here. And this x1 is now modulated by a parameter omega, this x2 by a parameter omega 2. Now, these are called weights. And you can think of these, if we are fitting a first order polynomial, you could think of these as the slopes in your first order polynomial. And then we are going to have something which we call bias, which is fed in here. We call this for b, and that's called the bias. And again, going back to the first order polynomial, this b is going to play the role of the intercept. And this gives us an output. So in this specific case, we have no hidden layer, but the inputs are being modulated or massaged by this function sigma, and then it spits out some output. And this is now the output layer. And I'm going to call the output for y tilde, as we did before. So this is now the output layer. This function, which you see, this sigma, has also a specific name, and I'm going to call this an activation function. Actually, what you see here is something which was inspired by neuroscience, because you can think of this circle as a neuron, and it receives an input, some signals, which are being modulated. And then depending on the values which you have, the neuron can send a new signal, or it doesn't send a signal at all. So you could think of this as a neuron which fires, depending on the electrical signals it gets from the other bystanding neurons, and then it sends a new signal to other neurons, or just sends one single signal. So this model is actually called the simple perceptron model, and it was already introduced back in the 40s, in the previous century. and it was seen as a kind of way to mimic the way neurons actually act. So it's something, this is the reason why we call these neural networks, is very much inspired by neuroscience. So you would typically see this quantity which we have here. This is normally called a node / neuron or / unit, activation unit or whatever. So I'm going to call these for nodes in general. That's the kind of notation which I will be using. And sometimes I'm going to call them for neurons, and sometimes it even happens I call them for units. But these are names which you will find in textbooks. Any questions so far? Okay, so if you look at what we have here, we are now going to rewrite this function sigma a little bit. And what we have is a function y tilde. So our y tilde now is going to be a function of this sigma, which now depends on x1, x2, and then w1, w2, and this parameter beta. Now I'm going to sandwich these terms here into this parameter theta, because these are going to be in my parameters of the theory. These are going to be the inputs, and I'm just simply going to replace them with an x. So this is going to be a vector. So this x quantity, which you see here, a little bit bold-faced, is actually a vector x1, x2 transposed. Now, a very simple model you could think of is actually something which runs like a y tilde, which is now given by this vector x. So we would have x transpose multiplied with these weights. So we define a vector weight, w. So these are the weights, and that would be given by w1, w2 transpose, plus this parameter b. So this is pretty close to what we have done before, right? So we have the design matrix, these x's, which contain the inputs. This is multiplied with the parameters. So if we are fitting a first order polynomial with only x1, then we know that this w is the slope, and b is the same as the intercept. So just think back to what we did with linear regression. Note also that what we have here is a linear model. So that clearly leads to some suspicion that if I want to have some non-linearity, what I have here on the whiteboard is not going to catch that. Okay? So these are just definitions which I'm putting up. So that means that with these kind of terms here, since these terms b is a part of the unknown parameters, so this becomes, so let's circle in these terms. These are the parameters now. So these are parameters, which we then sandwich into this quantity theta. So we have 3 parameters, and we have 2 inputs, x1 and x2. And then we have a series of outputs, which we then can use to train a specific model. So a typical example you could use now is the following. So let's take a closer look at that. And this is the reason why I'm bringing up these examples from electronics, is because this is a simple case where actually this kind of linear model, which you see here, and with this simple perceptron, fails dramatically on a simple case. So let's take a look at that. So the kind of example which we are going to bring in are examples from electronics. So this is normally what we call an OR, an XOR, and an AND gate. So if you now look at an OR gate, what you have then, you send in 2 inputs, x1 and x2, and they produce an output, which we then just call for the target. Now, what you would have then is the following. So if x1 and x2, they come in terms of zeros and ones, bit 0 and bit 1. So x1 takes the value 0, x2 takes the value 0, and this target takes then the value 0. And then you take 0, 1, and then you have 1, 1, 0, bit 1, and bit 0. This returns bit 1. And then if we have 1 and 1, it returns 1. So what I'm going to do after the break is to rewrite this as a linear regression problem. So, but before we take a break, let me just make a drawing of what we have here. So if I take x1 along the first axis and x2 here, we have 0 and 1, 0 and 1. So we have now 0 and 0, we have 0. If we have 1, 1, we have 1 here and here. So these are the values which I can get. So the question to you guys, before we take a break, could I use linear regression here to classify whether I have ones or zeros, depending on the input? So if you look at this, how could you use linear regression? You can actually do that. How could you use linear regression to classify correctly the outputs? So give that a thought during the break and see if I can trigger some kind of creativity here. But you could actually use linear regression to do this. And with linear regression, what it means is that we are going to try to make a model which actually, in our case, is going to look like this. So our y, now we have a y of I, that's the output from the model. So we could take this x1 for one of the states I, multiplied with w1, plus x2 for one of these events I, times w2 plus b. So just a small hint before we take the break seriously. So what kind of object would this be if you were to plot it? Yeah? Say it again. Just a line. So what I could do now is to find a line which divides the data. And then I could say value bigger than this, 1. Value lower than that, 0. I could actually do that. I could use linear regression to separate the two zones. So let's look at what we can achieve after the break. And now I'm going to put the recording on pause. And then we take a break and stretch legs a little bit.